Once upon a time, there was a son who was ordered by his dad to clean up his room. In that room, there was a bunch of strings and integers. And so, the son chose one way to organize it. The son just created a pile in the middle of the rug. To him, it seemed quite natural. You could still recover the strings and the integers from this pile. On seeing this, the dad was frustrated. He had a completely different idea for how to organize the strings and the integers. Dad argued that they should have been using a cabinet and labeling the drawers, and would be far more organized. But the son fought back. He said, "There's nothing you can do with your method that I can't do with mine. Besides, mine's already done. And therefore, I'm going to keep my solution." Smiling with some pride, the dad stood back and recognized that, in fact, what his son had built was a commutative diagram. Any two paths would get the same result. So he had been had. The son was allowed to keep his organization. He had, in fact, created a way to store both the strings and the integers in a way that no one could ever improve upon. The end. Commutative diagrams are actually hardcore mathematics. They're used in even PhD level mathematics. But at the core is something as simple as the picture behind us. This little allegory is trying to show us that it can be something where we're just thinking about moving information or data around, or even substances, as long as we get to the same results for any two paths. We're nudging towards category theory. It's an additional component to the study of any computational language. And that's partly because it's highly diagrammatic. It draws pictures that look somewhat like the flowcharts that you might find when discussing some kind of science or business problem. Because of the fluidity of the diagrams, we can communicate our ideas to someone else in a way that's reliable and translates well to the logic. Once we connect to the logic, we're on our way to making a program. We've already seen through things like the Curry-Howard isomorphism. Every logical operator converts to a data type, and that data type can be programmed so that we can do computations. So this is one of the key changes that we need to move towards the applications of our programs, matching diagrams with real-world situations. Now, to do that, we want to think of composition. The key thing in any kind of diagram involving functions is that we can put two ideas together, building small ideas that we trust to build more complex ideas that overall we trust because of the process. There are some rules, though. When we try to compose, we have to have some compatibility. Here I have two functions. If this is a data type A and a function turns it into a data type B, I can't necessarily use that data just anywhere. That creates contradictions, as we saw on our lecture on what are sets about. When we have the same data coming into a function G and converting to C, we are, however, in the perfect situation to take the results of F and plug them in to make new results from G. We call that the composition of the functions. We write it like this. G composed with F is that tiny little circle. There's also some language that you might see in programming because it's often the case that you can't program the little circle. So you might see words like this. It might be read as G after F or F before G. These are both ways to communicate that we want to glue them in a specific order. Keep in mind, composition is not commutative. You can't order really matters. Now, once we've done this composition, the key thing now is to see that we can draw a picture that can communicate to anyone else around us what we're doing with this composition as quickly as possible. And from that, maybe our nice designed flowcharts that we see in kind of studies of some science might translate into easy programming. So, what's the picture to draw? There really are three arrows on the board. One of them goes from A to B, another from B to C, and this last one we just created goes from A to C. What we should do is connect these like dots in a picture. Our function from A to B is an arrow from the first dot A to the second dot B. Our function G goes from B to C and is also an arrow. It's just a relationship of these dots. We forget about worrying about what the data is inside, and we just look at the flow of the information. The composition is a third line. That H goes from A to C, and it represents the function we just created, the composition G composed with F. Now, this picture will become so important that it's worth dwelling on it. What we want to do is draw a distinction between just simply matching up arrows and the arrows that actually come from composition. Here's what we need to do. If we actually follow this path, then it shouldn't matter how we get to the endpoint. As long as two paths get to the same place, they ought to give the same result. If I apply f to a little a, I can then apply g to that little f. On the other hand, if I look at composition and I apply it to that little a, the rules of composition tell us that g of f of a equals g of f of a. If we stand back and look, we see that we got to the same place. Either we took the long way around to get to g of f of a, or we took the shortcut and applied the composed function to get g of f of a. This is what's known as a commutative diagram. It's a diagram in which we follow the arrows around, and any two ways to get to the same point result in the same values. They must be equal. This is not true of every process you will see, and certainly there are plenty of flowcharts where the entire point is to see that there are shortcuts, other ways of doing things that might result in different things. Those are perfectly acceptable, but they don't have predictable results. If I write something where taking one journey or another is a different answer, then I can't simply say that I know what I did when I said I went from A to C. I would have to tell you in addition what journey I took. Commutative diagrams are the limited view of diagrams in which it doesn't matter. We're interested in the result, not the process. So we might even substitute a shortcut if we need to. When we have a commutative diagram, we want to tell our audience that it is a commutative diagram, one where you can go in any two directions as long as you end up in the same place. We can do this in a number of ways. Sometimes you might shade in the areas that commute. That's a favorite because it's visually impressive. You can see that these are now connected and glued together. But it's also difficult if you don't have the right device. So you can just write the words, they commute. But perhaps the strongest thing you can do is simply write the equation that's hiding behind what it means to commute. This commutative diagram has three functions, f, g, and h. And the composition f before g is the same as h. It's now an equation. Commutative diagrams are just a clever way to hide an equation. Equations are wonderful parts of mathematics. They're things that we can set up and solve. They're things that we can reason about. It's something that you've practiced many times. It looks like a polynomial. With enough time, you'll see this as a type of algebra. So when in doubt, write the equations out. But if you're like me, you might enjoy the occasional picture to go along with it, and it might help you connect to your fellow scientist. So, commutative diagrams of this kind are a special flavor of commutative diagrams because they tell a story. They tell a story that starts from some raw ingredients, create a new type of data, and then that new type is so special that if anyone ever challenges us with an alternative, we can show them that ours is as good as theirs, at least for the task being described. This universal quality of some commutative diagrams is ideal for programming. It means that we can plan for the future. We can make an architecture that someone else could then later say, well, what about this? And we can show them ours does that too. Or we could even trade. If they end up having something where ours can do what theirs can do and theirs can do what ours can do, then it's pluggable. We can use them interchanging and we can start to bring in new features. For example, maybe outside of this picture is the question of how much it costs. How much energy does it take to run your program? How fast does it work? How resilient is it to noise? Other questions that might matter. And so now we can start to interchange our choices based on these external qualities that weren't there when we first designed the solution. This is going to take an entire lecture, and we'll see that you can approach it with somewhat of the same playful storyline, where we think of a cartoon series in time. You have some ingredients given, you solve it one way, but then you further show that anybody else who could solve it would have to produce something no better than yours. That's the kind of solution that will last forever. We'll see that when we look at universal commutative diagrams. For now, I want to leave you with this simple story. Don't be afraid to have some fun with your logic. Try to think about ways that you're going to remember it. Draw little doodles. Little diagrams can still be scientific if properly labeled and if you agree to some ground rules. The ground rule we've applied here is the commutative assumption. Any two paths that get to the same place give you reliable results. That's an equation in disguise. Once you've created the mathematics that goes with your diagram is ready to be used in computational language. Don't be afraid to play artfully with your ideas. It'll get you further. Until next time.